Recording in progress.
Are you seeing my slides in full screen?
Yep.
Okay. All right. So let's start. So the title of this talk is called "The Least Square Kalman Filter and Our Research on SLAM." This is a part of the talk in this topic: rigid localization mapping and SLAM. So I have already done the check-in. So basically ask you a question about your current knowledge about least square Kalman filter and SLAM. So this is outline for my talk. I gave an introduction about least square and then talk about our research on SLAM using least square. Then I talk about extended Kalman filter and then talk about our research on SLAM using extended Kalman filter. Then I will talk a bit about the possible topics for the next 3-4 weeks for this reading group. So for least square, I'm starting from a very, very simple example. Maybe this is the simplest example of least square. Suppose X is a scalar to be estimated, and we have two measurements about X. For example, this is a building, the height of the building. And we have two measurements saying one is 100 meter, one is 110 meter. So in this case, what we can say is we have one variable, which is X, and we have two equations, and the two equations are contradicting. One equation says X equal to 100, one equation says X equal to 110. So what do we do at this situation? Of course, we can't solve the two equations, right? Because they are contradicting. But one way we can do is we can formulate the problem as a least square optimization. So we want X to be close to 100. We also want X to be close to 110. So we minimize the square of X minus 100 and this plus the square of X minus 110. So if you can remember this sentence in red in this today's talk, that's pretty much good enough. So basically it's saying whenever we have more equations than variables, then there's the least square problem. So we have more equations than variables. So we formulate this problem as least square. The solution is easy. For this case, we just take a derivative and make the derivative equal to 0. Then we get a solution, which is 105. It makes sense because we have two information, they are contradicting, and we kind of take an average. So this is a very simple least square problem, but I tell you the fact that least square, we have more equations than variables. Let's try to be more accurate. So when we say the two equations, so the more accurate way to say that is we have two equations like this. The first one is 100 equal to X plus noise. 110 is X plus noise. And this N1 and 2 are the measurement noise. And if we assume the noises are all zero mean Gaussian, for example, the first one has a variance sigma 1 square, second one has a variance sigma 2 square, then we have very clear equations, right? The two equations are very clear. We have noise and we know the level of the noise. And in this case, the two equations, we call them measurement model or sensor model. So in another word, we can say each measurement gives us one equation. And when we have more measurements than variables, then there's a least square problem. So in this case, we have two measurements, and each measurement has some noise, and we have only one variable. So this is least square problem. So from the previous page, we can see one information we didn't really use. We didn't just use the information about the accuracy of the measurements. So we know the noise in the first measurement has this variance. The noise in the second measurement has the sigma 2 square variance, right? So how does that influence the final estimate? Can we take into account those information? So first, I want to remind you again, we always assume Gaussian distribution, a Gaussian noise in the least square. And for a Gaussian distribution, for example, one-dimensional case, we have a mean value, we have a variance. And the one concept, if you haven't known yet, is called information. So the information of a Gaussian distribution is just the inverse of the variance in 1D case. Because the smaller the variance means the smaller the uncertainty. And the smaller uncertainty means the larger the information. So the information is the inverse of the variance. This is for 1D case. For high dimensional case, we have the inverse of the covariance metric, and we call it information metric. So this information metric plays an important role in the least square formulation. So how to do that? We basically use the information in each measurement as the weight for the least square. So we now have a weighted least square. So we have two measurements, Z1, Z2, and the information of the first measurement is 1 on sigma 1 square. The information on the second one is 1 on sigma 2 square. Then we use that as weight to get the weighted least square. So we have this weight in front of the Z1 minus X squared, the second weight Z2 minus X squared. When we have the weights, then we can basically consider the different accuracy of the measurement. And the solution of this is also simple. You just take derivative, then you will letting the derivative equal to 0, you get this solution. And you can see the solution is a weighted sum of Z1 and Z2. And the weights depend on the information, right? The more information you have, then the solution will turn towards that particular measurement. So weighted least square is more useful than unweighted least square. Another thing is we can also calculate the total information. So we have information from one measurement, we have information from a second measurement. We can calculate the total information with simply the sum of the two pieces of information. And when we get the total information, we can also calculate the variance of the final estimate, which is the inverse of the total information. So for weighted least square, we not only get the estimated value, we also get the uncertainty of the estimate. So this is a one-dimensional weighted least square. Tells you how we can use the information from the different measurements and formulate as a weighted least square. Now for a very general least square problem, it's given in this format. It's B minus AX transpose times B minus AX. Here X is the variable, X1 to Xn, and B, you can regard them as measurements. And A is a matrix. So you can see here we require M greater or equal to N. So normally M is bigger than N, but at least it has to be equal to N. And we have this solution given in this formula. Similarly, when we have weights, we can put the weight in between B minus AX transpose and B minus AX. So this P is a positive definite matrix. And then the solution is also given in this closed form. And besides the solution, we also have the covariance matrix of the estimate error. So we can calculate the covariance of the estimate as well. So you can see for least square, linear least square, or weighted linear least square, the formulation is very clear, the solution is clear, and the uncertainty is clear. So everything is in closed form. Now we look at the nonlinear case. When we have nonlinear case, the Z is still the measurement, and Fx is a number of functions. They are all nonlinear functions. And the least square is Z minus Fx transpose times Z minus Fx. So in this case, the measurement model is given by this. The S measurement is given by that, and it contains noise as well. So again, we have M measurements or M equations, and we have N variables, and M greater equal to N. So we have more equations than variables, then we can formulate the problem as a nonlinear least square problem. Just to remind everyone, if you really have any questions, just to stop me and I can explain more. But otherwise, I will go a little bit quick because it seems to me most of you understand all this pretty much. And for this nonlinear least square problem, one method is called Gaussian-Newton iteration. And the Gaussian-Newton iteration is obtained by performing linearization or the first order Taylor expansion. So we approximate the nonlinear function using a linear function. And then we can change the original problem as a linear problem. This X is variable. Then we can use a solution from the linear least square. We can get the solution of the nonlinear problem. But this one, because we are doing linearization, is not accurate. We need to do iteration. So we're starting from initial guess on the solution. This is x0, and then we use this iteration to calculate x1. Then we perform linearization at x1, then calculate x2. Keep iterate until convergence. So this is the Gaussian-Newton iteration. Now the general case is nonlinear weighted least square problem. And for the nonlinear weighted least square problem, we have M measurements. The function are all nonlinear, and we have noise. And we assume the noise follow a Gaussian distribution. And we put all the noise together and assume the whole noise vector following a Gaussian distribution. With zero mean and covariance matrix PZ. In the case when all the noises are independent, then this covariance matrix PZ will be diagonal. But in general, if they have correlations, the noise have correlations, you can have a non-diagonal covariance matrix. So this is a problem. We have M measurements and we have N variables. And the noise, the whole noise vector following a Gaussian distribution with zero mean. In this case, we can formulate the nonlinear weighted least square problem, which is given in this format. So you can see we put the inverse of the covariance matrix in the middle as the weight. So this is a weighted nonlinear least square formulation. And for the solution, we can again use Gauss-Newton algorithm. First, find the initial value, starting point, and perform iteration. And in the iteration, you can see the correction matrix PZ inverse is appearing in the iteration equation. So generally speaking, if we have m measurements nonlinear model and have n variables, and if the noises are following a Gaussian distribution, then we can formulate a problem as a nonlinear weighted least square, and we can solve it using Gauss-Newton algorithm. So how about for localization problem, mapping problem, and SLAM problem? So suppose this is scenario, and this R0, R1, R2 are the RoboPose at different time steps, and F1, F2, F3 are the features in the environment. For the localization problem, the variables we have are R0, R1, and R2, RoboPose. And the measurements, we have odometry, which is from robot 0 to robot 1, robot 1 to robot 2, and also the observations from robot to feature. Observation to the feature. For the mapping problem, suppose we know the robot position at all the time, then R0, R1, R2 are all given, then the variables will be F1, F2, and F3, the position of the features. The measurements will be, again, the observations from robot to the features. But in this case, we want to estimate the features. That's for the mapping problem. For the SLAM problem, we want to estimate both RoboPose and feature positions. And in this case, because all the information or measurements are relative, we need to fix a coordinate frame. Normally, we fix R0 as the origin, and then the variable will be R1, R2, F1, F2, F3. And the measurements contains odometry and observation. So in each case, we can see there are more measurements than variables. So in each case, we can formulate the problem as a least square optimization. Now I will briefly talk about our research on SLAM using least square. I mentioned only a few key papers we published. The first one is called Parallax BA, done by Liang and us. So in summary, what we can say is for this Parallax BA, what we have done is we choose a different variable, x. So the variable to be estimated is x, right, in the least square. We choose a different x. Then we formulate the problem and got a better problem to solve. And this is one we consider monocular SLAM. So the observation are the basically the image points. And we formulate the problem differently, mainly using different x. So, and we basically use the features, not using x, y, z, but we use parallax angles and other angles to represent a point feature. And this way, we come up with a much better optimization problem and with much better convergence. So basically, this piece of work, we are using a different x and got a good algorithm. We also have other work. For example, this first one is called DSLAM, decoupled solution to simultaneous localization and mapping. This one, what we are doing is we basically using different x and also different z. So what do we mean by different z? Basically, we transform the original measurement into a different format and use that new transformed measurement in the least square. So we're not only changing X, but we're also changing Z. And then we got a new formulation, and this new formulation has also good properties. Similarly, for the map running paper, we are also choosing different X and different Z. So what we did there is we first built the local map. And when we got the local map, we use a local map as a Z. So each local map is a new measurement. And then we formulate the map running problem as a new least square optimization. Furthermore, we have this linear SLAM. Again, we use different X, different Z. And on top of this submap running, we change the coordinate frame when we join the maps. And then we can result in linear least square instead of nonlinear least square. So all this work, I think these pretty much are three of my favorite works, using different variable X and different measurement Z and formulate different least square problem. There are many, many other papers as well, but I just want to mention these three here. So this is using different X and different Z in the least square. Another group of work is using special structure of this function fx. So in this nonlinear least square, there's a nonlinear function fx. And for SLAM problem, this fx has a special property. It's linear to some variables, nonlinear to some variables. It's mainly nonlinear to the robot rotations. And using this fact, we come up with different work and algorithms and others. One is from Kasra. It's also published in TRO about separable SLAM algorithm. So we use this special structure of this function fx. We also did some work using a different object function. So this is a standard object function, but we can have slightly different ways to define the object function, for example, using different norms and others. And then we prove that using different object function can make the problem different. And if we choose the object function properly, the problem can be easier to solve. We also look at the conditions when the solution to least square is reliable. So we look at the number of measurements, and the location of a measurement means basically the measurements is between these two variables. So we find out the tree structure have a big impact on this quality of least square estimate. So that's a paper in IGR done by Kasra. So that's some of our kind of papers published in the top journals. And they are all based on least squares. And I'm thinking we will be able to present some of them, maybe one or two, depend on your requirement. So I want to ask you for those works, what do you want to hear about this? And I have another question on Mentimeter. If you log in there, you will see this page. So we have parallax BA, which is using different X, and the decoupled SLAM using different X and Z. Yeah, others. So can you see this page? Yeah. So I just want to see your interest. Give you some very brief idea about what they are, and then you can tell us which one you're more. If more people interested in a particular paper, we can talk about that. Okay, it seems that the newer papers are more popular, right? So like published in 2015 onwards. Okay, so we have a like rough idea of what you want to hear. Okay, I will now talk about extended Kalman filter. Kalman filter is for estimating the state of a dynamic system. So for this case, we have a process model or the dynamic of the system. And there's also an observation model, which is a measurement of a function of the state. And both the process model and observation model have noise. And the noise, we all assume they are zero mean Gaussian noise. In Kalman filter, we assume the state follows a Gaussian distribution. And we estimate the mean value and the covariance matrix of the Gaussian distribution. So that's the Kalman filter. We only estimate the state, the mean value, and the covariance matrix, because we assume the distribution is Gaussian. And there are two steps in Kalman filter. The first one is prediction using the process model, and the second step is update, use the observation. Again, I want to give you a very simple example. I think this is probably the simplest example of Kalman filter. So just imagine there's a robot move on the straight line. This robot is a 1D robot. It doesn't have orientation, and the position is only in the real axis, which is one value, a real number. And the robot motion model is given by this. At time k plus 1, its position is the position at time k plus a control input, UK. You can imagine this UK is a control, it is a velocity, and the time step is 1 second. So the velocity times 1 second is the distance. So xk plus 1 is xk plus UK, and the wk is a noise. And we assume the noise has a variance of sigma u squared. The observation model, we assume is something like a GPS. It can have the measurement of the position itself. So the zk is just xk plus noise. And this noise is also zero mean Gaussian with variance sigma z squared. So we have the process model, we have observation model, and both the process model and the process noise and the observation noise follow Gaussian distribution with certain variance, zero mean, certain variance. And now, suppose the robot position at time 0 is 0. Then after move one step, the control is U 0, and the new estimate of this robot position will be with mean value u0, and the uncertainty will be sigma u squared. So at time 0, the position is perfect, 0, and when the robot moves, we know roughly it moves u0, and the uncertainty is given by this variance. So after the prediction, the robot state position for the Gaussian distribution. Now, after we have an observation, in this case, it's Z1. So when robot is already at time 1, so the observation is Z1. Then we use this to do the update. After the update, the robot position will be a weighted sum of U0 and Z1. Because one information tells you robot is at U0, another information tells you robot is Z1, right? So the new updated value is the weighted average. And the weights depend on the information. And also we have a variance. Variance is just the inverse of the total information. So if you still remember the weighted least square we talked about on slide 10, this result is actually exactly the same as the weighted least square, where we have two measurements. One is U0, one is Z1, and this first measurement has variance sigma U square. The second measurement has variance sigma Z square. Then the weighted least square gives you exactly the same result. So from this example, you can clearly see the connection between Kalman filter and this square. So roughly speaking, we can say the update step of the Kalman filter is the same as weighted least square. So this is a very simple example of Kalman filter. In general, for linear model, given this equation, and a linear observation model given by this equation, and we also have UK as a control, WK as a Gaussian process noise with coherence metric Q. And we have the measurement noise, which has coherence metric R. And we assume at the beginning, the state follows this Gaussian distribution, x0 hat and coherence metric T0. And starting from that, we can have prediction update. You can, starting from any value given mean value coherence matrix at time k, we can calculate the mean value coherence matrix at time k+1. Prediction step using the process model, and roughly speaking, you enlarge the uncertainty coherence matrix. And then when you do the update, you use the Kalman gain multiplied by the innovation. So innovation is the measurement minus expected measurement. And then your coherence metric kind of reduce. So this is a Kalman filter for linear system. For nonlinear system, we have nonlinear process model, we have nonlinear observation model. The noise are still assumed to be Gaussian. In this case, we have extended Kalman filter, which is given by, again, prediction and update. The main difference between extended Kalman filter and Kalman filter is we are using Jacobians. We're using Jacobians to calculate the coherence matrix. So for EKF, you can apply it in localization mapping, and SLAM. For localization, the state to be estimated is the robot pose at time k. Nothing else, just robot pose. That's localization. For mapping, we are estimating the features. And in this case, features has no dynamic. Basically, it's stationary. At time k and time k plus 1, they are the same. And for SLAM, we have robot pose at time k and also the features. So the process model is a combination of the robot model and the stationary features. So in all the cases, the observation model are the observation from robot to features. One practical problem for applying extended Kalman filter or least square to localization mapping of SLAM is data association. Data association is to identify one particular measurement is for measurement of which feature. And in this case, there are different ways to do this data association. A typical way of doing data association is look at this innovation. So innovation is Z minus H X bar. X bar is the current estimate of your state. So you calculate the difference between the real measurement and the expected measurement, assuming this measurement is on this feature. Then you can calculate this innovation. And in Kalman filter, we always calculate this innovation covariance, which is S. So if your innovation is too large, for example, more than 3 sigma bond of this innovation covariance matrix, then you will say, okay, this is not from this feature. And if this innovation is smaller than say 2 sigma bond or some threshold, depending on this innovation covariance, then you can say this is the correct measurement to this feature. And one typical method is called the nearest neighbor method. So you calculate the innovation and compare with this, get the gates, and the smallest one is a matched feature. So that's one way to do this data association. Another way to do data association, you can use like a shift or surf feature extraction and matching. And after that, you do some kind of ransack to remove some outliers and so on. So I don't want to talk too much details about the data association, but data association is a critical part for practical localization mapping in SLAM. Doesn't matter whether you use EKF or least square. For the least square, what we are talking about is a kind of offline approach. We already done the data association, but in real case, you need to do incrementally. Then you can get the data association done. So let's briefly talk about our research on SLAM using EKF. The first one is my paper in 2007. That's the paper with the highest citation of my paper. It's now cited more than 400 times. What we have done is we proved the convergence of EKF SLAM algorithm for the 2D cases. Disa has his EKF SLAM paper, but his proof is for the linear case. So he didn't consider the nonlinear case. What we have done in this paper, we proved the convergence for the nonlinear case. But we can only prove the result when the Jacobians are evaluated at the ground truth. And if the Jacobians are not evaluated at ground truth, we find out there's some inconsistent issue, and that makes the EKF SLAM algorithm not good. After 10 years, in 2017, Teng Zhang and others have published this paper in RAL. This basically is saying if we do the linearization on a Lie group structure, the consistency of EKF SLAM can be significantly improved. So we don't have to evaluate the Jacobian at the ground truth. We can evaluate Jacobian at the estimated value, and the consistency will be much better than traditional EKF. Very recently, we extended this work to object SLAM. So the features are not just a point, but the features are poses with point and also orientation. And we formulate this SLAM problem, again using invariant EKF, linearize it on the Lie group structure, and we demonstrate it can produce much better result than a traditional way of doing EKF for this kind of object-based SLAM problem. So we just complete this work and submit it to RL and this equal option for this year. Okay, so I still have a question. Which one do you want us to present? I'll probably do this survey later. So now the possible topics for the talks in the next 3-4 weeks. I think our plan is to have this rigid localization mapping and SLAM for 4 or 5 weeks. Then we switch to another topic. And after we finish all the topic, we may come back to this rigid localization mapping SLAM again. So we probably will talk for 4 or 5 weeks altogether. And this is the first one. So we will probably still talk about this topic for 3 or 4 weeks. So we really want to ask you for your opinion, what you want to listen for the topics, for the talks. So one possibility is talking about EKF SLAM. We have a TRO paper, RL paper. And we, again, the second option is we talk about least square based SLAM papers. And we can also talk about SLAM paper from other groups. But we would only talk about papers published in leading journals. And maybe others, because I don't know exactly what you really want to listen. It will be good if you can give me any suggestions on that. So I will probably do a survey there. So this is the 3 paper about EKF. Maybe you can tell us which one you want to listen. Yeah, the first one is a bit old, but it's probably the most fundamental one, and we can point out the problem. And the other one basically kind of solved the problem we pointed out in the first paper. Yeah, in most cases, if it's a first paper, probably I will present it because it's my paper. For the others, I think our student Sung Yang can present it. He's very good at invariant EKF now. He understands everything basically. So we can ask him to present. This is in general, like what you want to listen. One is the EKF kind of SLAM, one is the least square SLAM, one is some other papers or others, right? So what do you want to hear? More on least square, more on EKF, some other papers. Yeah, I will have another question to ask you about other suggestions or anything you want to say about the topics you want to listen. Yeah, seems the least square SLAM is the most popular one. So you probably know that this survey is completely anonymous. So, and we don't know who is selecting which, but yeah, you don't have to follow others' opinion. You can choose your own, right? So this is what do you suggest for the talks on rigid localization mapping and SLAM. Today I give you a very basic introduction about two fundamental techniques. So what do you want to hear? You can write anything. I think for this one you can write whatever you think, right? As a sentence or words. I haven't seen any answers yet. Can someone write something? You can say data association, for example, right? You can say I see the bar working now. Yeah. So one key message I want to convey today is, so you can see my publications of my work in the last more than 10 years, right? So we mainly use least squares, extended common filter to work on SLAM. So if I can say we are doing better than other people on SLAM, it's just because we understand more on SLAM problems. We understand more on least square techniques. We understand more on common filter techniques, right? So for doing high quality research, I think that's probably a key message. So you want to understand some techniques better. If you understand more about the techniques, understand the problem more, then you will be able to do some good work. Okay, I think based on your suggestions, we will decide what to do next week. Most likely, we will talk about some least square-based SLAM work we have done. Now, this is question time. I think I have a few minutes, but you can ask any questions, you can talk, you can also put in the chat, but the better way is to put your question here in this Mentimeter, then I will keep a record of that. And in case I don't have time to answer the question now, yeah, I can try to answer your question next time, maybe. Can someone write your question on the Mentimeter webpage? Just type something. I want to make sure it works, right? Okay, why EKF convergence is an issue on 2007? Yes. Okay, so the short answer is the linearization. When we have linearization error, then this EKF SLAM will give us overconfident results. I can spend a bit more time talking about some details next week. If it's very popular, we can talk longer. If not very popular, we can maybe talk 10 minutes or something just about why. So it's linearization problem. And if we say more clearly, is at different time, even the same features, same landmarks, is evaluated. The Jacobian is evaluated at different estimated values. So at time k, you evaluate the Jacobian at one state, and time k plus 1, you evaluate a different state. Then that inconsistency give a big problem. And someone proposed the first Jacobian algorithm, SLAM algorithm. Basically, they just evaluate at one first estimate value and don't change. And that performance is better than standard EKF, which is kind of surprising. I think we have another question. How can we get the mean and the current value of the Gaussian distribution in a specific problem? Yeah, that's also a good question. I think for the sensor model, for the measurement model or sensor model, we need to have understanding about the sensors, the quality of the sensors. And if it's not a Gaussian distribution, you can approximate the sensor noise as a Gaussian. Yeah, that's a sensor model. And for the estimates, we are using extended Kalman filter or least square to estimate the covariance rather than using measurement. Right? How has SLAM changed over the years and the impact deep learning has had on it? So deep learning is not my like. What to say? I'm not good at deep learning. Some of my students did a little bit on deep learning, but I haven't done much. I think deep learning is very useful for SLAM front end. So, for example, for feature matching, for object detection, it's very good if we can apply some deep learning algorithm to do that. But for the SLAM backend, like the estimation optimization, I have a feeling that it's not to the stage that we can simply using some deep learning to estimate that. So I would say front end is we can definitely use. Yeah, what can we do when things are very non-Gaussian? There's some SLAM work considering non-Gaussian distributions. For example, they consider the noise have a uniform distribution with a certain hard bound. In this case, there are some works, some papers on this, some of them published in top journals, but the computation complexity is a lot higher. So probably for small problem, we can get good results for that. For larger scale problem, still more research is needed for this non-Gaussian case. Now, which direction do you suggest to go, least square or EKF? Okay, we have been thinking EKF is not useful for like maybe 10 years. That's why we didn't really do much on EKF SLAM. But then when we realized there's an invariant EKF from 2016-17, we feel EKF SLAM is also good. So the key question is how well we can do using EKF. If EKF can get similar accuracy as least square, then EKF will be more practical because it's a kind of online and EKF doesn't keep the previous robot pose there. So for online practical application, if EKF can produce good result, I would prefer EKF. Least square can serve as a benchmark. So you can say what's the best people can do using least square. And another thing is there's some fast implementation of least square as well, like incremental least square methods, ISAM and others. So it really depends which one you want to do. But now we want to do more work on EKF based SLAM than before. How the process model is defined. How the process model defined. The dynamic is given by the physical system, right? How the robot move, how the feature change, and the dynamic, right? And the noise level depends on the sensor, right? So each when you have a sensor, you need to have some kind of sensor model there. And yeah, that's pretty much it. Okay, I think it's 4 minutes past 1. I will stop here. If you have any question, you can keep asking, and I can maybe answer next time. But we will discuss internally within our group. Maybe tomorrow, then we can decide what do we do next week. Thank you for coming. And if you have any suggestions on the topic or any other things, feedback, you can send me an email.
Yeah, thank you, Shoudong. Thanks a lot.
Okay, thank you.
Thanks, Shoudong.
Yeah, see you later.